The Big Bang model, our prevailing theory, describes a universe born from an incredibly hot, dense state, expanding for nearly 14 billion years. Evidence like the cosmic microwave background and Hubble's law supports this expansion, yet challenges remain. The Big Bang struggles with the singularity problem, the Horizon and Flatness issues, and the mysteries of dark matter and dark energy. Enter the Big Spin hypothesis, an alternative framework that incorporates space-time torsion, a twisting of the cosmic fabric. This hypothesis suggests that a Kerr black hole could transfer angular momentum to a new universe, potentially avoiding the initial singularity. Einstein-Cartan geometry explains space-time torsion, where spin acts as a source for this twisting, much like mass creates curvature. Crucially, this torsion could provide the explanation for the elusive dark energy, offering a new perspective on cosmic acceleration. Which one of these models do you think is closer to reality? Welcome to The Big Spin, a torsion-based, rotational genesis of the universe. Today, we'll explore critical deficiencies within the standard cosmological model known as LambdaCDM. This model, founded on the initial singularity and Big Bang expansion, necessitates extrinsic mechanisms to address key cosmological enigmas. First, the problem of angular momentum, or spin. LambdaCDM fundamentally fails to provide a natural, causal mechanism for the vast, universally conserved angular momentum observed across all cosmic scales. This fundamental oversight leaves a significant gap in our understanding of cosmic rotation, from stellar bodies to superclusters. Next, the inflationary requirement. Resolving the Horizon and Flatness problems mandates the inflationary paradigm, an observationally unverified, exponentially fine-tuned expansion phase. This theoretical construct is needed to establish the observed homogeneity and isotropy of the universe, yet it lacks direct observational proof. Finally, the dark sector enigma. The model requires that approximately 95% of the universe's mass-energy budget be attributed to unknown dark matter and dark energy. These serve as mathematical placeholders for unresolved theoretical tensions, highlighting the model's reliance on unobserved components. These critical deficiencies underscore the need for new perspectives in cosmology, like the torsion-based rotational genesis.
The Big Spin hypothesis proposes a paradigm shift. The universe was not born from a chaotic explosion, but was inherited from a state of controlled rotational symmetry. We postulate our universe emerged from the internal geometry of a highly massive, rapidly rotating primordial Kerr black hole. The Kerr metric avoids a true point singularity, featuring a ring singularity. This ring singularity conserves the fundamental angular momentum, denoted as J, which defines our cosmos. This hypothesis offers a new perspective on the birth of our universe, moving beyond the traditional chaotic explosion model. It suggests a universe born not from randomness, but from an inherent, conserved rotational order. The foundational metric, birth from the primordial Kerr black hole, a truly epic and mysterious origin.
Cosmic genesis is defined by a controlled quantum gravitational permeation. Instead of collapsing to a point, the immense mass, energy, and, critically, the conserved angular momentum of the progenitor system are ejected through a geometric aperture, a white hole or wormhole gateway, into our new, expanding space-time. This is a transfer of inheritance, where the primordial matter is intrinsically seeded with motion. From t equals 0, our space-time is simultaneously infused with a fundamental, global rotational field derived from the progenitor's conserved angular momentum.
The inherited angular momentum manifests as a pervasive, subtle torsion field. This torsion field is derived from the intrinsic quantum spin of the primordial particles within the framework of Einstein-Cartan gravity. This field provides a preferred axis of alignment, directing the initial condensation of matter. Unlike standard models where structure forms randomly, the intrinsic rotational symmetry acts as an architectural bias for subsequent structure formation. Structure formation proceeds under gravity in a rotating medium. The globally conserved angular momentum dictates that matter condensation is not random. Instead, primordial matter preferentially clusters and aligns along the streamlines of the angular momentum vector. This naturally generates the observed cosmic web filaments and ensures that the early protogalaxies inherit a coherent incipient spin, directly resolving the long-standing problem of cosmic spin origin.
The kinematic origin of Hubble expansion. The Hubble expansion is redefined as a geometric consequence of the global rotation. In this framework, the observed Hubble parameter is the direct manifestation of the universe's overall angular velocity. The enormous magnitude of this global rotation means its radial kinematic component presents itself exactly as the accelerated expansion of space. Thus, h0 is proportional to omega.
Welcome to an exploration of one of cosmology's greatest mysteries, dark energy. We'll delve into how it might be resolved geometrically through the advanced framework of the Einstein-Cartan theory of gravity. The Einstein-Cartan, or EC, theory offers a profound generalization of Einstein's general relativity. It expands our understanding by allowing spacetime to possess not only curvature, but also an additional property known as torsion. This concept of spacetime torsion is not merely theoretical. It is dynamically induced by a fundamental property of matter, the intrinsic spin, or quantum angular momentum, of elementary particles. Imagine this spin-induced torsion field as a long-range, repulsive geometric force. It's this force that generates the precise accelerating effect we've attributed to dark energy, pushing galaxies apart. This elegant solution, often referred to as the Big Spin model, fundamentally transforms our perception of dark energy. It moves it from an enigmatic unknown to a quantifiable, geometric phenomenon. Ultimately, the Big Spin model reveals dark energy as an intrinsically linked effect of cosmic matter's rotation, offering a unified and geometric explanation for the universe's accelerating expansion. This geometric resolution provides a compelling new perspective on the universe's evolution, inviting us to reconsider the very fabric of space-time and its profound influence on cosmic dynamics.
In conclusion, we delve into a truly unified rotational framework that redefines our understanding of the cosmos. The Big Spin hypothesis presents a comprehensive cosmological framework meticulously constructed upon the fundamental principles of conservation of angular momentum and the intricate geometry of Einstein-Cartan torsion. This innovative hypothesis offers natural and elegant resolutions to some of the universe's most profound mysteries, including the unexplained origins of cosmic spin and the necessity for cosmic inflation. Furthermore, it sheds new light on the enigmatic nature of the dark sector, providing a coherent explanation for dark matter and dark energy within its rotational paradigm. This compelling model suggests a universe fundamentally defined by intrinsic rotational symmetry, where every element participates in a grand cosmic dance. It envisions a vibrant, dynamic cosmos, eternally bound to the angular momentum inherited from its progenitor, a universe born not from chaos, but from a precise and beautiful geometric dance. The Big Spin hypothesis thus offers a profound and elegant perspective on the universe's structure and evolution, inviting us to reconsider the very fabric of reality.